most of the universe is dark. Most of it is filled with this stuff that's invisible and untouchable, yet everywhere. And we call it dark matter. My main focus of my work is dark matter. That's what I usually study. But then there's a new player in the game. That's pretty recent. And that's black holes. Supermassive black holes in particular, like the one at the center of our galaxy that we just got an image of in May. I'm assuming that you've seen that. If you haven't, it's the one on right over here. That's the black hole at the center of our galaxy. And then the other one here is the first image that we've ever gotten, which was in 2019. That's in a galaxy that we very nicely call it M87, because that's what astronomers do. Now, the difference between the two is that the black hole at the center of our galaxy is 4 million times the mass of the sun. That's a lot. But the other one is over 1,000 times that at 6 billion suns. Okay. And these things seem to sit at the center of every single galaxy across the universe. And that, what you're looking at right here, it's not stars. Those are supermassive black holes. This is an image taken in radio. So those are all these are all supermassive black holes at the center of galaxies. All the galaxies that we've observed that are massive like ours have supermassive black holes in them. And we use telescopes to do that. And telescopes are really cool because they're like real life time machines that we can use to look back in time at our universe. Oh, yes. Thank you. Thank you for that. Sorry about that. Okay. Telescopes are like real time machines that we can use to look back at the history of our universe. Everything that you look at, even the sun, you're looking at as it was in the past, because light takes time to travel through space. So it takes time to reach us from where it is emitted. So for example, when you look at the Andromeda galaxy, which is 2.5 million light years away, that just means that a light year is the distance that it takes light to travel in 1 year, and that's about 9 trillion kilometers. Okay, so it's a lot. And the Andromeda galaxy is 2.5 million light years away. So every time that you look at Andromeda, either naked eye or through a telescope, you are seeing it as it was 2.5 million years ago. Not as it is today, but as it was 2.5 million years ago. And we've looked further than that. We've looked way back in different wavelengths. We've looked as far back as before when the universe was younger than 1 billion years old. 700 million years to be exact. And when I say exact, I mean it's there's no exact there, but when we do that, we find supermassive black holes that far away too. The problem with that is that these supermassive black holes weigh 1 billion suns when the universe was very young. Too young that we don't know how to explain that. We just don't know how they grow so big so fast. What if I were to tell you, that dark matter and black holes might be the answers to each other's question? So as in the question of supermassive black holes, how do they grow so fast? And the question of what dark matter is. Using them combined, we might be able to answer both of those questions. So today, what I hope to tell you, I'm hoping that you leave here with a bit more some knowledge about what black holes are and what dark matter is or what it isn't, and that you maybe take away some analogies from here that you can use at parties, and and anytime that you look up into the night sky, that you can also take it in and look at it and just acknowledge that, wow, what I see is just a tiny fraction of what's actually out there. So now I would like you all to just take out your phones. Hopefully you have an internet connection, and just type this in. It's all these. I have 3 polls today. They're all fun. Okay. So it's just to get an idea of what you all think. This one's about black holes. What I'm asking here is, what do you think of the options that I've listed? What do you think black holes would lead to if you were to cross into one? And I'll give you about 45 seconds for that. Okay. If it's not working for you, is it because you're on an Android phone? Are you using like a native Android browser? Oh, it is yes, it is case sensitive. Yeah, it is case sensitive. Okay, that's a bit more than 45 seconds. Has everyone had enough time to punch that in? We'll look at these results at the end. Okay, so imagine filling your bathtub up with water and then pulling the stopper. What'll happen is that your water will start to drain down into the drain. Well, the universe is filled with these kinds of sinks, and those sinks are black holes. You can think of them in a similar way. You get too close to a black hole, and you're going to go in. If you cross too close, there's no coming back. So black holes are essentially what happen when you take way too much mass and cram it into a really, really, really small point in space. The gravity, force of gravity takes over, and then it starts to go into a never-ending collapse into this thing called a black hole. And this is something where the force of gravity is so strong that if you come too close to a black hole, you're not going to be able to escape it. Not even the thing that travels the fastest, which is the speed of light in a vacuum. Light travels the fastest in a vacuum. Not even that can escape it. That's how incredibly strong the gravity is of a black hole if you get too close. They also, if you've heard of the term singularity, what that means is that you get sort of like an infinite density at this region in the center. But in physics, infinities are actually like problems. They tell us that there's something wrong. Okay? So that's a problem. And Einstein realized that as well. So when Einstein wrote his theory of general relativity, his friend Carl Schwarzschild went and he went working on his equations and stuff like that. And he came back to Einstein and he said, hey, I actually figured out these things, I figured out these solutions to the equation, which give us black holes, but black holes that's not what they called them at the time, not just yet. And Einstein was like, no, that doesn't make sense. You can't have infinite density. Infinities just don't make sense. And nobody believed in black holes at that time. Okay. No one believed in black holes, and they just thought it was like a sort of a glitch in the equations, and they just brushed it off. But after Carl Schwarzschild worked out the equations, he also ended up working out something called the Schwarzschild radius, which you might have heard of as an event horizon. And that is the point of no return. It's also the point, like if you were to take it tells you what sort of the radius of the sphere that you would need to take some particular mass, and crush it into that sphere. That's the radius of the sphere you'd have to crush it into. Now, a bit later in the game, a physicist by the name of John Wheeler coined the term black hole. It turns out that it was actually a student that mentioned it, but he thought that it was a very good way to refer to these things, and black hole became a thing. And then another few years later, in 1971, a few astronomers actually detected a black hole by the name of Cygnus X1. The one that I've listed here is one that's from Toronto, just like myself. Well, actually, he's from the US, but he did this in Toronto using the Dunlap Observatory. Okay, and I've gone to the Dunlap Observatory. It's awesome, and so I just listed him because I'm a proud Torontonian, and so. Okay, so we know what the Schwarzschild radius is. So let's try to calculate it. These are my hamsters, Charmini and Muini. I name my hamsters after subatomic particles. So Charmini is named after the charm quark, and Muini is named after the muon. I will say that this measurement was taken in, I think, about March. Charmini is definitely bigger than this now. Okay, she's grown a lot. So she's probably going to be more like 55 to 60 grams, whereas up here it shows 43.5 grams. And Muini is probably, she grew maybe a little bit, so she's maybe like 35 maximum. But when you plug it into this equation, it's not too important about the details, but the mass of the object that you want to plug, that you want to like see what its Schwarzschild radius is, meaning that how much do I have to scrunch this stuff in order to make it turn into a black hole, becomes something so tiny. 10 to the minus 29. That's a 1, okay, 1 over a 1 followed by a 29 zeros. It's incredible. It's incredibly tiny. Let's go to something a little bit more sensible like the Earth, okay? The Earth is huge. And even then, if you wanted to turn the Earth into a black hole, you'd have to cram it into such a small, like a sphere of such a small radius that it's only 9 millimeters. So it would be about like maybe 2 centimeters across, like a marble, essentially. The sun, 3 kilometers. Then there's this really, really, really massive guy in the universe, okay? It's the most massive black hole that we've ever measured so far. It's 66, it weighs 66 billion suns. So it's huge. And that, the Schwarzschild radius of that is pretty gigantic. 1,300 times the Earth-Sun distance. So it would swallow our solar system over and over. At least up to Pluto. Now, just to kind of, I guess, give you an idea of what the magnitude of these measurements is. The radius of an atomic nucleus, which we cannot see, obviously, is 10 to the minus 15 meters. So my hamsters are not going to make very good black holes. And that's great, because we're not going to try. And the distance of Pluto from the sun is 40 times the Earth-Sun distance, which we call an astronomical unit. So 1,300 times that is pretty huge. That's a really gigantic black hole. So let's talk about some masses. So there are some, you might have heard of something called a primordial black hole. We don't know if those exist, but if they do, these are ones that would have formed in a very early universe from just the density fluctuations through space-time. Okay, we don't know if they exist yet because we've never detected one. But a stellar mass black hole, so one that's several times the mass of the sun, is something that forms when some of the most massive stars die. Okay. They fall into a never-ending collapse and a black hole is left. A step up from that is intermediate mass black holes. And these are anywhere from like 100 to 100,000 times the mass of the sun. They form from, they start from like stellar mass black holes, and then they accrete. When I say accrete, it just means eat. anything that goes too close to a black hole and falls into that event horizon is accreted mass. And mergers, which we've seen from LIGO detectors, like the gravitational wave, merging with another black hole. And they merge, they grow into bigger ones, and you get these intermediate mass black holes. Then finally, we get supermassive black holes, over 100,000 times the mass of the sun. We don't know how they formed. Okay, if they were to start, the only way that we know that black holes, or the only way that we know of that black holes begin to form, that we're sure of, is from the death of stars. And so if we were to begin with a star, or a black hole that came from the death of a star, so several times the mass of the sun, it's very difficult to get to a supermassive black hole by either eating matter or by mergers like this. And the problem with supermassive black holes is, again, that we find them very early in the universe's history. It's not so much that we find them near us. It's that the universe was too young. There wasn't enough time for them to grow that big. And that's one of the biggest problems in physics. We don't know the answer to, in astrophysics and cosmology. We don't know the answer to it yet. We don't know how supermassive black holes formed. Now I'm going to ask you all to try this again. It's another poll. This one's about our friendly dark matter, this invisible stuff that's everywhere in this room, and we can't touch it and we can't see it. I'll give you again about maybe 40 seconds. Okay. All right. Something really strange is happening in galaxies. Something really strange. Galaxies and galaxy clusters. They're behaving really weird. And we've known this for years. Stars seem to be moving too fast in clusters of galaxies, which are essentially hundreds to thousands of galaxies that are gravitationally bound together. We also see galaxies moving too fast in these clusters. None of these things should remain together. They should be flown apart. They should have flown apart by now at their speeds. And Fritz Zwicky in the 1930s, in 1933, looked at the Coma cluster of galaxies. That's a cluster that is, I think, 330 million light years away from us, so it's pretty far. And so when he looked at the Coma cluster, he saw that things were just moving too fast. This is a galaxy cluster that could not, with all the matter that we can see at that, so just the stars and stuff like that, with that matter, it couldn't hold all these galaxies together in this gravitational potential. They just would have flown apart. And so Fritz Zwicky he's Swiss, and so he coined the term dark matter, but he coined it in Swiss. So it was Dunkel Materie. I'm 100% sure I did not pronounce that correctly, but it translates to dark matter, and that's where the term comes from. So we've known this stuff is around. We've known it for so long, but we still haven't been able to detect it yet. The problem then, though, when Fritz Zwicky took these measurements, he did it at a time where we didn't know distances to objects very well, because when you measure distances, you need the expansion rate of the universe. The universe is expanding at an accelerating rate. We need to know how much it's expanding by in order to be able to tell how far things are. At that time, the expansion rate we had was very large and it was very off, translating to a very off distance as well. So that, along with the fact that in galaxy clusters, you actually have 10 times the amount of mass in gas that you do of mass in stars. And we didn't have good data back then too. So these things translated to an error of about, I think he overestimated it by like 10 times. And eventually it was just kind of like forgotten. Nobody took him seriously. He also wasn't a very nice person. So nobody wanted to be his friend and nobody wanted to take his stuff seriously because, you know, that's kind of how it is. You gotta make friends in the field. But he didn't do that. And yeah, he overestimated it greatly. But then in the 1970s, someone came along by the name of Vera Rubin. And she, along with Kent Ford, pointed the telescope over towards the Andromeda galaxy and started to take data down. Started to take data down and found that he was right. Like, this is actually a thing. There's dark matter in this. Like, there's something going on. And in fact, her measurements were so good that they're still applicable today. They're still applicable today. It's not just in galaxies, in stars, in the speeds of stars. We find this evidence in things like in other things like gravitational lensing. So a gravitational lens is Einstein's theory of general relativity. Essentially says that mass bends space-time. The more massive an object, the more it'll bend space-time. So think of like placing a billiard ball on a mattress versus placing a bowling ball on a mattress. The bowling ball is going to bend that mattress a lot more. And similarly with space-time, that happens too. Galaxy clusters are very massive. So they're going to bend space-time a lot. And so if you happen to have a galaxy that is way behind that cluster, it should be hidden from our sight, because photons of light, rays of light in space, in the vacuum, travel in straight lines. They just travel in straight lines. And if you have something blocking it, you're not going to be able to see it, right? Unless the space-time around it is bent, so that you get the rays of light kind of bending around the object because space-time itself is bent. So those lines are itself, the photon, like the rays of light are actually traveling in straight lines, but they're traveling in straight lines along bent space-time. And so you get these really cool features like arcs and stuff like that, depending on where that galaxy is. This is a galaxy that's very far away behind that mass. And then you get these arcs like what you see in this image. And the amount by which it's arced, like the amount, like the size of it is what tells us how much mass there is in that galaxy cluster. And there's way more than all the stars and all the gas. Remember, gas makes up 10 times more mass than the stars do. All of that is just not enough to explain these. We also see it in a baby picture of the Big Bang. It's the cosmic microwave background. It tells us how much dark matter there is. And it also tells us that there was a time in the universe, because what we see today, we see this large scale structure. So basically what we see in the universe today required that we had dark matter fall into some dense region. So just to give you an idea of what represents, the red points are where regions that are more dense. But when I say more dense, I'm talking about a difference in like one part in 100,000. So it's very small, but they translate to something big over time. Okay. So we know that dark matter exists. We still can't detect the thing. And we've been trying. My hamster friends help me out a lot. Now, this is like all the hamsters that I've had. You'll notice that the neutrino, his name was Neutrini. He's in all three of those because neutrinos actually oscillate flavors, so they go from one to the other. And so the reason why I'm showing you this, it doesn't really, the details don't matter, but what you're looking at, aside from the beyond standard model part, what you're looking at is essentially the particle physics, the particle physics version of the periodic table of elements. But this is for particles, so the most fundamental particles that you can get from matter. Everything that you see, like any interaction that you see, the fact that I can simply touch this, the fact that you can see me and that I can see you, that happens because there are forces to bring these particles together. The strong force is the reason why we have protons, which then with neutrons come together to form atomic nuclei. Without the strong force, we wouldn't have them. It's the strong force that keeps them together. And then the electromagnetic force is what holds electrons in to atoms as well. And so any interaction that you have, if you were to take two billiard balls and scatter them off of one another, if they scatter, there's a force acting there. If there wasn't a force, they would just not see each other. They just kind of go through each other like two ghosts, okay? So one way to look at it is think of like a Lego structure that you make of Lego. You break it down to its most fundamental constituents, and you're going to get little Lego blocks. If you were to take any object, if you could break it down to its most fundamental constituents, you'd end up with subatomic particles. Now, with Legos, if you look at the studs, you can think of those studs as forces. Because the force is there, I can put it together. It can interact and create something bigger. Okay? Without those, it just wouldn't stick, right? So that's what the forces do, holding these particles together to make objects like this clicker and like this mic. So then think about dark matter and picture like a block that's just solid. No studs, no gaps for you to put anything into. So it can't interact with the other piece. It can't attach to make something bigger. It doesn't see it. But it's even more than that, because when I say it doesn't see it, it means it should just pass right through it. So in reality, dark matter, because it doesn't interact with the same forces that we do, passes through us like we don't exist, because we need a force in order for something to interact. And so dark matter is just like us, except these two really key, or this really key thing, that it just simply doesn't interact with the same forces that we do, aside from gravity. Okay. So the most commonly used model of dark matter is one that actually says that dark matter particles don't have any forces, so they don't see each other. They're like, imagine if you were to take two billiard balls, launch them towards each other, and they pass through each other like ghosts. There's no force to interact with the other particle, okay? But in my work, I study the possibility that there are scatterings, so that dark matter particles do actually scatter off of one another, similarly to the way that you would see two billiard balls that you launch towards each other. Exactly what you would expect is to scatter, and that's what what I think, what I'm trying to see if whether dark matter does. And that would mean that it would need a force to interact through. It's not going to be the forces that we know. So it's going to be a new force, a new dark force. That scattering is actually really important. It changes some things. When you have like a gravitational system, so a system bound together under gravity, if you include scattering, where particles colliding with each other exchange energy, you end up with this sort of beautiful, magical thing where this interplay between gravity and collisions that I call the colliding gravitational waltz ends up doing something really, really neat. Every collision that a dark matter particle faces in a halo, in a dark matter halo in a galaxy, will bring it closer in to the center of that galaxy under gravity. And that keeps happening over and over again until eventually you have so much stuff in the center that you form like a black hole. And to show you what this kind of looks like, I'm going to use my ball of yarn, which I crochet with. And incidentally, this is one of the pieces of yarn that I use to crochet a galaxy cluster. So it's very fitting. I'm going to put this over here just for 1 second. Yeah, thank you. So think of this as maybe. So let's just think of this as a particle, a dark matter particle that is orbiting in a galaxy. If I take a particle and make it orbit, then this is what happens. And then I'm gonna cause a collision. Okay. What happened? This particle lost energy and fell towards the center of gravity, which in this case happens to be the Earth. Fell down towards it. But in orbiting systems or systems that orbit under gravity, like galaxies do, these particles have momentum, so you can't just drop into the center. So what they do is fall in closer and closer and closer until you have so many particles so close to each other that you end up maybe hitting that Schwarzschild radius that we talked about and forming a black hole. And this can only happen if you have scatterings, right? Because if I didn't scatter, if I didn't like introduce my fist in that case, which was going to be another particle that it scattered off of, it would just keep going. Okay? But the scatterings cause it to lose energy and fall closer in to the center of the galaxy. How excited are we about this? The James Webb. Yeah. Yes. And so am I. Because the James Webb Space Telescope, or let's call it the JWST, okay? The JWST sees in infrared. And the really useful thing about seeing in infrared is that it can infrared pierces through dust and clouds. So that if you were to look, say, like at a nebula, you'd be able to see more stars than you would in visible light. What it can also see is wavelengths that have been stretched beyond the visible wavelength due to the expansion of the universe. These are objects that have been stretched beyond our vision. Like we can't see them anymore. But the JWST is gonna look at exactly that wavelength so that it can capture the first galaxies and maybe figure out whether dark matter black hole seeds can be formed. And if it turns out that that's true, the black holes that would form from these dark matter halos would be seeds that we can use to explain how we actually find black holes that weigh 1 billion suns only 700 million years after the Big Bang. They won't be the mass of the sun, or they won't be the mass of several suns. They'll be more like 10,000, maybe even 100,000 suns. So at that point, we can explain supermassive black holes. You might be wondering why it matters. What is it going to do for you? What is it going to do for me? What's it going to do to find out what dark matter is? This stuff that's so obscure that we can't even see, we can't even touch it. Like, what is it going to do for me? Medicine, if we have medical advances, we can lead to cures. It gives us treatment. So we know that's something that I can get. If we figure out fusion, many other things include we'll have a source of energy that is clean, and a way to travel in space that's a lot more efficient than what we have now. But dark matter, something that doesn't even interact with us, what's it going to do? It's the question. And I can tell you this, and this is true. Like, I can tell you that it's because humans are curious and we want to know things, and this is a mystery, and it's great to uncover this stuff because it's something that we want to know. And that's absolutely true, because I can tell you that when I was a child, one of the things that fascinated me, even though I didn't know that I wanted to do this as a career, I was always fascinated by black holes, because we couldn't explain everything, because the singularity was something we couldn't explain. Dark matter that we didn't understand, dark energy that we also don't understand, or understand even less than dark matter. But that's not it. At the heart of the matter, it's possibility. Opening the doors to possibilities. What are our oops. This is one last poll. So another 40 seconds, and then and then I'll continue. Okay. That poll might tell you a little bit about where my mind is at. Possibility. What are our current possibilities? With the current technology that we have, we reached so far that we put footprints on the moon. We put footprints on the moon. We sent out a piece of giant space origami 1.5 million kilometers away from the Earth. Sent it into space to unfold on its own. It could fail over 300 ways, and we did it. The JWST. We also inhabited a planet with robots. We got Mars covered in robots. We can't send humans there though, because we don't have the protection that we need. We don't have, in space, you're subject to a lot of radiation, dangerous radiation. And going to Mars, going to Mars takes 7 months. If we were to want to even think about going to Titan just to explore it, if we had radiation, if we had the protection, it would take us 7 years with our current technology. 7 years to get to Saturn, Titan's moon, or Titan, Saturn's moon. We need new technology. Now, why am I even telling you this? Like, why does it matter? I'm not going to tell you that discovering dark matter is going to help us figure all this out. We don't know. I don't know. But what I can tell you for sure is that dark matter, if you remember the slide that I showed you, where we had a standard model along with something called beyond the standard model, where there was like dark matter particles, those are things that our laws of physics currently, like the standard model, do not predict. Dark matter is not predicted by the standard model. So discovering it would literally rewrite everything that we understand. It would change everything that we understand, change all of physics. We'd have to rewrite textbooks. And what comes along with that? Possibility. It opens a door to possibilities we never had before. So at this point, maybe if I can ask if we can check the results of our surveys. Okay, so we have a significant amount of people who think it's invisible matter with mass. Okay, matter stuck in higher dimensions. It's a really cool thought. Don't know, but I want to find out. That's me. I don't know, but I want to find out. But I do think it's invisible matter with mass. I just don't know what. Can we check the? Death by spaghettification is the lead right there. And I can just tell you that if you wanted to avoid that, you know where you would go? A supermassive black hole, like Cooper did in Interstellar. Fusion drives. Okay. Most of us think fusion drives and safely visit Mars. That makes a lot of sense. I hope for wormholes, but I don't think that we'll have them that soon. And I don't know if we will, but those are my favorite method of space travel. I just wanted to see what you all thought. If we can bring back the slides, and thank you. So in summary, black holes, supermassive black holes exist way too early in the universe's history for us to be able to explain. And they're in all galaxies. Dark matter's everywhere. If it collides through a dark force in this colliding gravitational waltz, then we might be able to form the black hole seeds that would be able to explain all the supermassive black holes that we see in the center of every galaxy. The reason why it matters is because we'd learn about the properties of dark matter, which leads us even closer to uncovering what this stuff is. Right now, we know an awful lot about what it isn't, but we don't know what it is. That would lead to new physics and simply open doors to possibilities that could change the world. Thank you.
All right, we're going to be doing Q&A now. For this, we're going to need three microphones. So Sophia, if you don't mind, you can stand here and use this microphone. I will use this microphone at the computer, and we'll have a volunteer going around with a microphone to have your questions asked. We will also be taking questions from online, and I will, after the audience here asks their question, I will ask it again so the people online can hear it as well. So let's try this out. If you have a question here in the crowd, please put up your hand.
Hi, I'm just wondering if there's any sort of theory about why the expansion of the universe is accelerating and if dark matter is related to that.
Mm-hmm.
So the question is, the universe is accelerating. Does dark matter have anything to do with that?
Our best, or the most prominent theories tell us that dark energy is something that is causing the universe to expand at an accelerating rate, and that it's like a constant. One thing that we've noticed in recent times is something called a Hubble tension. So the Hubble constant is what tells us what rate the universe is actually expanding at. And measurements taken in different ways, one being the cosmic microwave background, others being like supernovae and stuff like that, give us different measurements. They give us really widely different measurements. If it turns out that dark energy is actually variable, one possibility is that it could be that dark matter, let's say, decays. And when I mean decays, I mean that it kind of breaks apart into something smaller, okay? And if that happens, then you have like kind of like less gravitational force pulling back on stuff, and then it would lead to maybe like a change in the Hubble constant. But other than that, there's really nothing that dark matter and dark energy have in common, except for the name dark.
Great, thank you so much. I'll take a question online, and that is, have we found as many intermediate mass black holes as predictions suggest should exist? Indeed, have we found any, such as in the centers of globular clusters?
Yeah, I think so with globular clusters, that's something that is an ongoing study. And we found intermediate mass black holes more in the like several hundred times the mass of the sun, and those have been detected by LIGO. Those were formed by mergers of smaller mass black holes. There's still this range that we don't have, like say in the 10,000 times the mass of the sun kind of range. We don't have those, and so we are not predicting as many as we would like.
Now let's take a question from the crowd.
First of all, thank you for the wonderful lecture. So one thing I have a difficulty to understand is that, as you said, that when these dark matter particles they scatter with each other, then it loses energy and it goes towards the center of the galaxy. So, but I'm assuming that there will be multiple such scatterings, and some of scatterings will, instead of the particles from losing energy to gain energy, then on an average, shouldn't nothing happen, and most of the particles should remain far away from the center of the galaxy.
So it gets there's a little bit more, like, I guess, meat to that story, but generally, like, the way that you can think about it is it's not really that a particle is losing energy so much as it's exchanging energy to another. And when it does that, it can send that particle that it's exchanged energy to out into the outer part of the halo. So that particle is no longer playing like a role in this. And because it's imparted that energy over to another particle, it has less energy and falls closer towards the center of the galaxy. And if that continues over and over again, then you end up with a lot of mass at the center.
Great. I will take a question from online. What is the ratio of dark matter to the known universe?
Okay, so in our universe, the amount of stuff that we have, we kind of look at it in terms of like energy. So the energy density, a huge amount of it goes towards dark energy. That's stuff that's causing the universe to stretch apart faster and faster with time. That's 70% of the universe's energy density budget. 25% of that is dark matter. And the remaining tiny little 5% is us.
Okay, great. We'll take another question from the audience.
Hi, my name is Miguel, and this is such a great honor. I just want to ask, how does dark matter expand, and how is it identified?
How does dark matter expand, and how is it identified?
So, I'm assuming that in terms of expand, we're thinking like expanding due to the acceleration of the expansion of the universe. And so dark matter behaves in the same way as regular matter does. It's just stuff that has mass that doesn't interact in the same way that the kind of matter that we can see and touch does. And so in general, what we know is that when you look at things that are expanding away due to the expansion of the universe, these are things that are not gravitationally bound to each other. So let's say a gravitationally bound collection of stars like a galaxy. Because the force of gravity is so strong, the galaxy itself is not going to expand. Similarly with a galaxy cluster, because that's also a gravitationally bound collection of objects, the force of gravity will be stronger, and so it itself will not be expanding or growing with the expansion of the universe. But clusters from other clusters that are not gravitationally bound to each other would be expanding away and from each other with the expansion of the universe. And dark matter behaves in the same way because it sits in the same way that regular matter does.
Awesome. Let's take another question from online. That question is, Sophia, is your work mostly based on math or observations, or kind of a mix of the two?
Yeah, it's a bit of a mix of the two. I never do observations myself. I'm usually sitting on my laptop doing some math, a lot of coding. If no one's told you that doing physics or astrophysics requires a lot of coding, it requires a lot of coding. So that's usually what I'm doing. My lab is my laptop, so it goes with me everywhere. And so I do that. I work out equations as well, and sometimes it's complemented. Let's say I want to like see whether my theories or what I'm looking for, it matches data. So in that sense, that's how I work with data, if that makes sense. Observations.
Awesome, that's great. Let's move to another question from the audience.
Thanks, Sophia. Going back to your original idea of that supermassive black holes from early universe would be made up of dark matter. That means dark matter from billions of years ago. But space is dynamic. Would you also be saying that, thinking that dark matter is somehow being created or brought into existence on a cosmic kind of basis?
So the question is basically, is dark matter being brought into existence somehow?
Everything that we have in the universe was created in the Big Bang. So all the dark matter would have been created from that budget. In some, I guess, depending on which model we look at, dark matter is essentially the lightest particle that you can get from decays that can no longer decay. And this would all have happened in the very early universe. So by the time we're talking, there's a freeze out. So at that point, Like in the very early universe, there's kind of like an amount of dark matter that's set, and that's it. That's what the universe gets. So you're not creating any more dark matter afterwards.
Great. We'll move to another question from online. Could you give some more details about the observations or evidence that tell us supermassive black holes of 1 billion solar masses existed only 1 billion years after the Big Bang?
700 million years after the Big Bang, even less. Yes, quasars. Quasars. These are, so quasars are essentially objects that are like black holes that are accreting a lot, so they glow really, really, really bright. We only seem to find them in the very early universe, and this comes from quasars as well.
Let's move to another question from the audience.
So you said that you could look 700 million years back. How far do you think we could eventually see? Like to the Big Bang or something?
The question is, how far back in time can we look?
That's a great question. So in fact, we've actually seen further back than that already. The picture that I showed you of the cosmic microwave background, that's when the universe was only 400,000 years old. But it's a different wavelength. So we need to use different wavelengths in order to be able to probe different parts of the universe. But what I can tell you is that in terms of like visible light, or even any kind of light, so even in the radio wavelengths, it's all light, it's just different energy. We can't see further than the cosmic microwave background. And the reason for that is because when you go further back, the universe is in a much sort of, it's much smaller, it's in a much more hot, dense state, so that photons bounce off of other matter. And so it's kind of like it's opaque. You can't see it. Kind of like if you were to look at the sun, in the sun, photons are bouncing off of other matter all the time. And so, you don't want to look at the sun at all, but you can't see through the sun for that reason. It's opaque. It's going to be kind of similar. So we'll never be able to see beyond in light at all. One way we might see further is with neutrinos, but that's it.
Great. We've got a few questions online that kind of relate to each other. So it's kind of, if you can summarize a couple things here. Somebody asks, what is the distinction between dark matter and dark energy? And somebody asks, what's the difference between dark matter and normal matter? And could you please briefly summarize the known characteristics of dark matter? So it's kind of, I guess it's a kind of a summary type set of questions.
Great. So, okay. Dark matter and dark energy. Let's start with that. Dark energy is stuff that's causing the universe to expand at an accelerating rate, meaning that as time progresses, it stretches the universe apart faster and faster. We understand it very little, very little. Whereas dark matter is actual stuff, just like what this clicker is made of, but it doesn't interact with the same forces that the stuff that this clicker is made of does. So it can't come together and combine. It can't reflect light so that you can't see it. It doesn't interact, and so you can't touch it. So essentially, dark matter is mass. Dark energy, stuff that's stretching the universe apart. That's one. The second question, if you can.
Just the difference between dark matter and normal matter.
Yes. So, and dark matter and normal matter, I kind of answered that right now. The difference between the two is simply the interactions that they have, the forces that they interact with. Normal matter is subatomic particles that interact with specific forces that bring them together to form atomic nuclei and atoms, and so on and so forth. Dark matter is also a subatomic particle, but one that doesn't interact with the same forces that normal matter or us, we do. And so that's the difference between the two.
And the last one was just summarize the basic characteristics of dark matter.
Okay, that's a great question because I can tell you very little about it, but we're increasingly knowing what it isn't compared to what it is. And so this is what we do know about it. We know that we can't see it because we would have seen it by now. So it doesn't interact with the electromagnetic force. which also means that it doesn't have a charge. It's neutral. It's electrically neutral. We know that it doesn't interact with us because it doesn't interact with the same forces, and we can't touch it. And we also know that the way that it had to behave in the early universe was that it had to be moving slow compared to the speed of light. So it had to be moving slow compared to the speed of light, meaning non-relativistic. And the reason for that is it had to have enough time to be able to come together and coalesce under gravity to form seeds that would be massive enough for matter, regular matter, after the universe expands and cools enough that photons are no longer bouncing off of regular matter and pushing regular matter out. Then normal matter can fall in towards those seeds that were made from dark matter and create the universe that we see today.
Awesome. Let's have some hands up in the crowd. Take another question.
What would happen if dark matter didn't not exist?
The question is, what would happen if dark matter did not exist?
Yeah, great question. If dark matter didn't exist, you could still end up with a universe of galaxies. It would not be the galaxies that we see today. We wouldn't have like large structures. We'd have sort of, I guess, a different looking universe. You'd have less small galaxies, like the dwarf galaxies. And so it can form a universe, but it would not be the one that we can see today. And one of the main things is that we wouldn't be able to create the large scale structure that we see and the uniformity that we see as well.
That's great. We've got a question here online related to thermodynamics, which I find scary. Don't tell Eric Donovan I said that. I'm looking at Chris, don't tell him. If black holes are formed by colliding dark matter particles, what can you say about the temperature?
It wouldn't be anything special. So dark matter it's hard to comprehend it because it's such an obscure thing. But dark matter is no different than regular matter. It's just stuff that interacts with gravity and nothing else. Once it forms a black hole, that's it. It's a black hole. It doesn't matter anymore. So there's no difference really between the two.
Cool. Let's have some hands up again in the audience. We got one lined up.
Hello there. Great talk.
Thank you.
Also, a general question about black holes, I guess. Now, we're always told two different kinds of concepts. Black holes, spherical, mass and spin, and then the drain kind of model, where it's, just disappears into whatever. So, what is the better type of way to conceptualize them? Both? There has to be one. There has to be both.
Okay, so no, I can see why it's confusing. The real problem with that is the fact that our minds can't really think in 3D. So when we resort to like analogies like the drain or a mattress that bends, for example, those are analogies that are two-dimensional that we can understand. But if I were to tell you that in you have to kind of imagine in 3 dimensions, which because it is like, I mean, it's a 3-dimensional object. It's hard to visualize it. And that's really where the problem is that our brains just can't really comprehend something beyond that. So we go down we project it to the two-dimensional analogies. That's where the drain thing comes from.
Cool. Let's go back online. Here's a great question that I find fascinating. Is there dark matter on Earth or in our solar system?
Yes, that's a great question indeed. And yes, there is. In fact, there's dark matter in this room right now. My hand just passed through a bunch of it, just like this. It's passing through every single one of you too. So the answer to that is yes, dark matter is everywhere.
Great. Let's go to another question from the audience.
Hi. When CERN was doing its shenanigans, people were worried that they're going to make black holes that would take out everybody. They would be very small. So my question is, would a hamster squished black hole take out a bunch of people, or would you need like a dog or possibly a dinosaur? What's the size of animal you have to squish to start to cross the machines?
So the question is, what size of animal would you need to smush to create a black hole?
Okay.
Yes, I'm serious.
So that's great. That kind of brings up this mechanism, or this thing called Hawking radiation. It was theorized by Stephen Hawking. What it says is that over time, black holes evaporate. And the smaller a black hole is, the faster it evaporates. But I mean incredibly fast when you get to those kind of sizes. So a hamster size, or, you know, a black hole that you can create from a hamster size would just vanish. Not instantly, of course, because there's no instantaneous thing, but it would vanish so fast that it would just do nothing. In order for a black hole to be able to do something, I mean, it would have to be huge. Look, the whole Earth, it would take the whole Earth to create a black hole that would just be 9 millimeters in diameter, or sorry, in radius. So all those things that people were saying it's not a concern. It's not a concern because you couldn't make a black hole that big.
Great, thank you so much. And we'll probably take questions for another 10 minutes. For those of you here, Sophia will be around after the end of this presentation to be able to ask your questions. But let's move to another one that's online. You said that if there is a dark force that enables dark matter particles to interact, collide, or scatter, then the dark matter particles will lose energy, and the dark matter cloud will relatively rapidly collapse under gravity to form a supermassive black hole. Since energy is conserved, why do scattering dark matter particles slow down? Where would that energy go?
That's a great question. And I answered it in another question that was from the audience. So it's not really that the dark matter or particle loses energy. It's that it exchanges energy and gives it off to the other particle that it's collided with. So energy is conserved. It's just been given to a particle that's now shot off into the outer regions of the dark matter halo.
Great. How about another one from the audience there? Perfect. Got one right there in the back.
Hi, my name is Stella. Is there less dark matter and dark energy expected near large planetary bodies versus more dark matter and dark energy located much further away from these large planetary bodies? Of course, this will affect space travel imaginations, if that's truly the case.
Okay, great question. So dark energy is essentially uniform. It's everywhere. So it has nothing to do with you know, whether there's a galaxy here or you know, a planet here. The one thing that does make a difference is if there's a collection of stars, they're gravitationally bound to each other. So the dark energy is unable to overpower the gravity, and so the galaxy itself doesn't expand. But the dark energy is still the same. It's the same throughout, no matter what. Now, dark matter, it's the way that it's I guess distributed in a galaxy, for example, is that because in the center of a galaxy you have the most mass, you kind of think of like the gravity being like a bowl. And so things want to fall to the center of the bowl. So you're going to have more like a denser amount of dark matter near the, like, closer to the center versus further out. Planets don't matter. They don't.
You're saying that it's uniform everywhere. It sounds more like, you know, soil, substrate, something found everywhere, but it's superstitious things, like with the, and streams and so forth, like, how would you view it?
Yeah, so dark matter is definitely everywhere. It will kind of clump up in certain regions, so you'll find a lot of it in galaxies. For example, you'll find more in galaxies than you will outside of galaxies. But if you were to zoom out of the universe and look at it as a whole, then it looks uniform.
Great. Let's move on to a question that's online, and I think it's time to get a little philosophical. If we are hit by a car, we get hurt, but we cannot be hurt by a car if it is made of dark matter. Is that true?
Yes, but I'll also say that we don't know if we can make a car out of dark matter because we don't know if dark matter has the forces required to create, to combine to make things like atoms and stuff like that, that would then form an object like a car. We don't know that it does.
Good answer. And I guess that answers my question of if a tree of dark matter falls in a forest, does it make a sound? Let's go to another question. You know what? Let's move to another question online, and it's probably our last question. And this is a really fun one. Could a tiny universe at the time of the Big Bang explain why bigger black holes existed? Black holes colliding and gathered earlier on.
Can you repeat the question?
Sorry, could a tiny universe at the time of the Big Bang explain why bigger black holes existed?
Could a tiny universe?
Yeah.
Oh, okay. Now I think I understand because I guess the question is if the fact that the universe was small would make a black hole seem bigger, I guess, more massive. But we're talking about mass, we're not talking about size. So that wouldn't be why. Can I just say something? There was a question over here.
Oh yeah.
There was a question over here. Yeah, I saw. Oh,
What would happen if there was no dark matter or normal matter?
What would happen if there were no dark matter or normal matter?
we would live in we wouldn't live, but the universe would be very boring. We'd have nothing but light particles, and so you couldn't form actual stars or anything like that. So it would just be a universe that was just extremely boring.
Awesome. And you know what, we'll do one more question. And that is, Sophia, what inspired you to pursue your area of study? What would you tell young people who are interested in pursuing study in astrophysics?
Okay, this is a great question because as a child, I actually didn't, I'm one of the people who didn't know that I wanted to do astrophysics. I didn't know that that's what I wanted to do. So I thought I was going to be a medical doctor. That's the sort of thing that my dad put into me, like, yeah, you got to be a medical doctor. And so I thought I was going to do that. And then as I grew, I realized I couldn't handle blood, and I'm like, no, I'm not going to do this, and I need to go and find out what I want to do. So I enrolled in university as an undecided major, fell upon an astronomy club that I started to attend, and I fell in love. It's not the only way that I knew that I liked this stuff. I've known since I was a child, like I would go, my mom would take me for meteor showers and, learning about dark matter being everywhere and we don't know what it is, all this stuff, and dark energy stretching the universe apart faster and faster with the progression of time. These are all things that fascinated me. I just didn't know that that's what I wanted to do. And so the way that I found out was by joining an astronomy club. So I would recommend that you do that. If that's something, like, join an astronomy club, because no matter whether you want to do this as a career or just for fun, it's amazing. It's amazing. You go to star parties, you get to hear about, different lectures and stuff like that. So you learn a lot of things. And so what I would say, do that and go for it. If this is something that you want to do, and if you don't know what you're looking for yet, then this is one way that you can find out. It's how I did. After the astronomy club, I enrolled in the astrophysics program.
Awesome.